What does Jupiter hide? Today, we venture into a world of giants, where the winds howl endlessly and lightning tears through the skies. Jupiter, more than just a planet, a celestial legend. From ancient temples to today's laboratories, it fascinates, it intrigues, it dominates. What do we really know about this colossus? And why, among billions of twinkling points, have our eyes settled on it? But before we embark on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a nice trip. In the vast tapestry of humanity, Jupiter is one of the first celestial objects studied by humanity. Around 2000 BC, Babylonians, Greeks, and Chinese observed it with the naked eye, fascinated by its brilliance and slow progression. Some, endowed with exceptional visual acuity, claim to perceive dark zones on its surface. Despite limited means, these observations fueled divinatory practices, influenced agricultural cultures, and fed the fascination for this star brighter than many stars. The Babylonian Emul-Apin tablets, which cataloged constellations, placed Jupiter among the major stars. The Babylonians had identified its apparent cycle and tried to determine its synodic period, that is, the time separating two returns to the same configuration relative to the Sun and the Earth. Better understanding this rhythm allowed them, they thought, to anticipate political upheavals, climatic uncertainties, or harvests. For them, divination and agriculture formed a whole. Understanding the sky was preparing for the realities of the Earth. In Greece, it was associated with Zeus Phaethon and called the morning star or evening star, depending on its position. Chinese astronomers incorporated it into the stars of the ages and followed its movements to assess the stability of imperial power. The movements of Jupiter carried political and religious importance. They were signs of the stability of the power in place. Some observers claim to discern 4 dark bands on the surface of the planet, long before the invention of instruments capable of confirming it. Perhaps on nights of exceptional clarity, the contrasts of its atmosphere were perceptible to the naked eye. These famous belts, alternating with lighter zones, are well known today. This anecdote shows how much the enthusiasm and concentration of the early enthusiasts could reveal far more than one would have thought. Early observations suggested the presence of dark bands on its surface, a detail later confirmed by astronomical instruments. A major turning point occurred on January 7, 1610, when Galileo, using a rudimentary telescope, discovered its 4 main moons, Io, Europa, Ganymede, and Callisto. This revelation supported Copernicus's heliocentric theory and shook established dogmas. Soon after, other scientists turned their attention to Jupiter. In 1665, the Englishman Robert Hooke observed a giant spot on its surface, known since as the Great Red Spot. This colossal storm, still active 3.5 centuries later, testified to a dynamic atmosphere. At the same time, others noted variations in the thickness and color of the bands, revealing a world far more complex than imagined. In 1676, a major turning point occurred thanks to Ole Rømer. By observing the eclipses of Io, he noticed that the time at which they occurred depended on the relative position of the Earth. By comparing these shifts with the estimated distances, he calculated for the first time the speed of light, a revolutionary discovery, showing that light took a certain time to travel through space. Starting in 1690, astronomers took an interest in Jupiter's rotation. Giovanni Domenico Cassini at the Paris Observatory established that the planet did not rotate uniformly. The summit of the clouds completed a rotation in 9 hours and 55 minutes, but this period varied according to the latitudes. This phenomenon, unique to gaseous planets, revealed a unique internal structure, quite different from that of rocky planets. Around the same period, Edmund Halley had the idea of using the moons of Jupiter to navigate at sea. By noting the precise moment of an eclipse, sailors could calculate the exact time at a given point and then compare it to their own measurement to deduce longitude. This principle, difficult to implement but promising, marked a major advancement in navigation. It also paved the way for astrometry, a discipline dedicated to measuring the positions and movements of celestial bodies. Jérôme Lalande published nautical ephemerides, providing sailors with reliable tables for their observations. At the end of the 18th century and throughout the 19th, the study of Jupiter intensified. As early as 1781, scientists began analyzing the light coming from the planet. Spectroscopy made its appearance, allowing for the identification of the composition of its atmosphere, which is mostly made up of hydrogen and helium. Even though the instruments were still rudimentary, these efforts opened a new era in the understanding of giant planets. In 1850, the first daguerreotypes of the Great Red Spot were made. Photography, still in its infancy, required long exposure times and delicate preparation. Despite their blurriness, these images proved that it was possible to capture the faces of the sky. They were the starting point of a long visual adventure, destined to perfect itself over generations. In 1878, the American astronomer Asaph Hall, already renowned for his discovery of the moons of Mars, formulated a bold hypothesis. Jupiter might be surrounded by a ring. He claimed to have distinguished a barely perceptible diffuse halo that suggested a belt of dust. Due to a lack of sufficiently advanced instruments, he could not provide proof, and the idea remained confidential. It was only several decades later that the existence of a faint ring, formed by debris from small satellites, would be confirmed. "16 years later, in 1894, James Keeler at Lick Observatory managed to capture detailed images of Jupiter's polar bands and their subtle color variations. These images, obtained thanks to advances in astronomical photography, encouraged a more rigorous monitoring of the Jovian atmosphere. Month after month, scientists compared the images, tracking changes in the arrangement of clouds, the color modifications of the bands, and the metamorphoses of the Great Red Spot. This patient work, shared among observatories, helped create a more precise portrait of the planet. Between 1895 and 1955, a new chapter opened with the emergence of radio astronomy dedicated to Jupiter. At the beginning of the 20th century, the very idea of listening to the sky seemed fanciful. However, in 1932, Karl Jansky, an engineer in a telecommunications center, detected a strange signal at about 20.5 megahertz. Initially thinking it was a terrestrial disturbance, he eventually identified a celestial source, Jupiter. This unexpected discovery showed that celestial bodies could emit radio waves, and that these signals revealed unprecedented information. The announcement sparked the interest of enthusiasts. One of them, Grote Reber, built a makeshift radio telescope in his backyard, equipped with a metal dish and a custom-designed receiver. In the 1940s, his observations confirmed the existence of powerful emissions associated with Jupiter. These signals, known today as synchrotron or decametric emissions depending on their nature, revealed the intensity of the planet's magnetic field and the agitation of charged particles in its environment. Faced with these revelations, scientists began to imagine a model of the Jovian ionosphere, an atmospheric region traversed by electromagnetic interactions. Due to its size and the strength of its magnetic field, Jupiter appeared vastly different from Earth. To better understand it, analyzing the radio waves proved invaluable. It allowed estimating the temperature of certain layers, measuring electronic density, or following cyclic rhythms related to rotation. Although rudimentary, these initial models laid the groundwork for a more thorough physical exploration. Thus, from antiquity to the brink of the space age, Jupiter has always inspired admiration and inquiry. From Babylon to ancient China, passing through Greece, people have turned their gaze toward this moving light. The discovery of the Galilean moons in the 17th century was a true upheaval. The idea of a universe centered on Earth was shaken. The appearance of the Great Red Spot, the methodical study of eclipses, and the calculation of the speed of light thanks to Roemer's observations showcased the efficiency of rigorous observation combined with reason. The following period saw the emergence of new ideas. The differential rotation of Jupiter, the use of its moons as navigation reference points, or the compilation of ephemerides to guide ships testified to an expanding scientific spirit. With spectroscopy, we began to probe the gases enveloping the planet. Each advancement opened new fields. The first photographs, Asaph Hall's experiments, Keeler's images, and the first steps of radio astronomy revealed a planet much more complex than imagined. Thanks to Jansky and Reber, Jupiter ceased to be merely a visual object and became a source of measurable emissions. It possessed a voice, and this voice spoke of a world in constant activity. By 1955, Earth already knew numerous truths about Jupiter: its 4 large moons, its rapid rotation, the dynamics of its clouds, the strangeness of the Great Red Spot, and the existence of radio waves emanating from its upper atmosphere. These advances, the fruit of centuries of effort, laid the foundations for a new era. Humanity was preparing to cross an unprecedented frontier, that of space exploration. An adventure that, from Babylonian tablets to modern telescopes, would finally lead us to a direct encounter with the giant of 100 faces. In 1955, while the world was immersed in the Cold War, approaching Jupiter was still a dream for scientists and strategists. The United States and the Soviet Union were competing in the field of science and technology, seeking to assert their power through increasingly ambitious space programs. This era, marked by the space race, was dominated by the first achievements in Earth's orbit or around the Moon, but it already translated into a growing desire to explore the planets of the solar system. In this atmosphere of tension, the United States began to consider, as early as the late 1950s, bold projects that seemed to push all limits. Among them, sending a spacecraft to Jupiter, the most massive of planets. Gigantic and distant, this gas giant fascinated astronomers with its unique characteristics. Visible to the naked eye as a very bright point, it remained surrounded by mysteries. It was in this momentum that NASA was born, founded in 1958. It relied on a network of research centers where increasingly powerful rockets were designed, along with more precise measurement instruments and probes capable of going well beyond Earth's orbit. Engineers, scientists, and decision-makers collaborated closely, aware that each space success reinforced their nation's image. Exploring Jupiter was not only a technical challenge, it was also a leverage of prestige in the ideological confrontation of the time. In this context, the idea of a series of missions to the outer planets took shape. there was talk of the U.S. Ranger Jupiter plans in connection with the Ranger program, designed to send probes to impact the moon while transmitting high-quality images. But some visionaries were already considering extending this technology beyond the moon, all the way to Jupiter. The United States began to think about designing probes capable of surviving a longer journey, equipped with telecommunications adapted to immense distances. Engineers analyzed the numerous challenges: more powerful engines, efficient power systems, and navigation capable of guiding a craft through millions of kilometers or miles. Yet obstacles hindered these ambitions: lack of budget, shifting political priorities, technical limitations. The Jupiter projects remained on paper while attention turned to the moon, the strategic priority of the moment. During this time, between the late 1950s and the mid-1960s, knowledge about Jupiter progressed through ground-based observations. Radio telescopes began to pick up signals from the planet, revealing the probable existence of a strong magnetic field. No missions were yet launched toward the giant, as the necessary technical means were lacking. The launch of Pioneer 5 in 1960 allowed for the study of space between Earth and Venus. But the idea of improved versions of this probe to reach the farthest regions of the solar system was beginning to take hold. Gradually, the notion of a trajectory beyond Mars, all the way to Jupiter, was gaining ground. In the 1960s, NASA developed the Pioneer program to explore increasingly distant regions. The Pioneer 6 to 9 probes, launched between 1965 and 1968, studied the solar wind and interplanetary medium. A decisive step was approaching, to definitively exit the sphere of nearby planets. It was in this dynamic that Pioneer 10 came into being, the first probe designed to fly by Jupiter and record its data. It was equipped to withstand much more intense radiation than in the rest of the solar system. Its components were protected by reinforced casings, its antennas sized to transmit information from hundreds of millions of kilometers or millions of miles away. Pioneer 10 was launched on March 2, 1972, from Cape Canaveral. Emotion was palpable. For the first time, a spacecraft was leaving the zone of the inner planets to head toward the regions dominated by the giants. The mission leaders knew the probe would traverse unknown territories, where every parameter remained uncertain. Yet, everything unfolded as planned, and it was hoped it would follow its trajectory, withstand solar eruptions, and avoid micrometeoroids. It sped towards Jupiter at an impressive speed for the time. The year 1973 was marked by a historic advancement. In November, Pioneer 10 reached Jupiter's environment. It was the first time humanity would gather direct data from such a distant planet. The teams had meticulously prepared for this approach. The trajectory was calculated to the millimeter, the instruments calibrated. The cameras, simple but effective, were to capture the light reflected by the planet. Other sensors, dedicated to magnetic fields, particles, and cosmic rays, were ready to probe the invisible. The magnetic field of a planet functions like a giant magnet. On Earth, it deflects particles coming from the sun and protects our atmosphere. The space where this field dominates is called the magnetosphere. When Pioneer 10 entered Jupiter's, the measurements exceeded all expectations. The magnetic field was 20,000 times more intense than Earth's. This staggering figure revealed the existence of an internal magnetic engine of unimaginable power. In a planet composed mainly of hydrogen and helium, this hinted at an internal functioning radically different from our own. But another discovery caught attention: The plasma ring of Io. Plasma is a state of matter where atoms, highly excited, break down into charged particles. In Jupiter's environment, this energy is fueled by its interaction with its moons. Io, in particular, underwent extreme gravitational forces. Its volcanoes expelled enormous amounts of material, which became trapped by the planet's magnetic field. The result, a massive torus-shaped plasma ring encircling Io's orbit. Invisible to the naked eye, this phenomenon was detected for the first time by Pioneer 10, which measured the density of the particles and confirmed their ionized nature. At the time, the discovery of a plasma ring around Io sparked immense interest in the scientific community, revealing just how dynamic Jupiter's environment was. The surveys showed that Io's atmosphere was partly the result of intense volcanic activity, and that the ejected materials dispersed into space in the form of ions, subsequently channeled by the lines of Jupiter's magnetic field. For specialists, it was a glaring proof. A satellite could shape the nearby environment of a planet, and vice versa. It was also understood that Jupiter's magnetic field was not a simple static shield, but a funnel where particles swirled, concentrated, and stretched with the rhythm of its rotations. The observation of this disk of particles was, however, just a glimpse into a set of phenomena that are still largely unknown. The instruments on Pioneer 10, limited by the technology of the time, provided only a partial view of the plasma structure, but this initial flyby paved the way for more ambitious missions. By proving that it was possible to send a probe that far, collect data, and transmit it back to Earth, Pioneer 10 turned the dreams of the previous decade into concrete reality. This success revitalized NASA, which launched Pioneer 11, then prepared the even more advanced Voyager probes in the second half of the 1970s. Such success would not have been possible without the technological and political fervor of the Cold War, which accelerated research. The budgets allocated to space agencies, scientific competition, and the desire to outdo the Soviet Union led to major advances, of which Pioneer 10 remains one of the brightest examples. Although its sensors were rudimentary compared to current standards, they provided researchers with radically new insights into the nature of Jupiter and its surrounding worlds. At that time, scientists were laying the foundations of comparative planetology. They aimed to establish links between data collected at Jupiter and those obtained on Earth to better understand the interactions between magnetosphere, atmosphere, and geology on a very large scale. The Earth seemed tiny compared to Jupiter, and this contrast heightened the fascination while refining our understanding of planetary physics. Understanding a gas giant was not just a matter of curiosity, it was also a way of retracing the history of the solar system's formation. Jupiter, probably the first planet to have formed around the Sun, thus became a key piece to better grasp the mechanisms of this genesis. Its magnetic field, moons, and rings fueled a broader reflection on the events that occurred in the solar nebula billions of years ago. In early 1974, as Pioneer 10 continued its journey beyond Jupiter, it left behind a treasure trove of data. The encounter with the giant planet in 1973 lasted a few days, punctuated by close-up measurements, light recordings, and radio emissions. Yet, the impact of this brief visit was felt for decades. Researchers analyzed the measurements to better understand variations in the magnetic field, the composition of the plasma around Io, and the effects of the solar wind, abruptly distorted by Jupiter's mass. They highlighted the scope of the Jovian radiation, dangerous for future satellites or human crews, and decided to equip subsequent probes, such as Voyager 1 and Voyager 2, with more effective shielding. Between 1955 and 1973, a dream took shape, developed, and became reality thanks to Pioneer 10. The dream of approaching Jupiter, probing its colossal forces, observing its moons. The entire phase of the U.S. Ranger Jupiter plans, that never launched, constituted a testing ground that, although unfinished, forged the spirit of future missions. The determination to push technical limits and outdo Soviet power played a crucial role in the advancements made in propulsion, telecommunications, and scientific instrumentation. Pioneer 10 thus embodies a decade and a half of efforts, trials, and progressive breakthroughs. By crossing Jupiter's magnetosphere, the probe confirmed the correctness of these choices. By revealing a massive plasma ring resulting from Io's volcanism, it showed that nature often surpasses predicted models. This discovery went far beyond a simple theoretical validation. It proved that near a moon like Io, volcanism could fuel a complex system of electromagnetic phenomena. For the general public, the image of a tranquil giant planet gradually faded, replaced by that of an extraordinarily active world whose magnetic influence extended over millions of kilometers or miles. In 1973, for astronomy enthusiasts, Pioneer 10 represented a true initiation into great planetary explorations. Other probes would follow its path, going even further towards Saturn, Uranus, Neptune, then to asteroids and comets. But it must not be forgotten that it all began at that precise moment when the rivalry between the blocks generated a momentum of progress that made it possible to reach the confines of the Jovian domain. His major discoveries, including the measurement of a magnetic field 20,000 times stronger than Earth's and the observation of Io's plasma, laid the foundation for our modern understanding of Jupiter. They also helped prepare future NASA missions to this fascinating world, from Voyager to Galileo and then Juno. The scientists of that time could congratulate themselves on having turned ideas into action, offering humanity a first glance at the gigantic forces at work around the largest planet in the solar system. The most notable discovery remains that of active volcanoes on Io, the colorful moon. As the probe photographs its surface, specialists notice plumes of material rising several kilometers or miles above the ground. Spectral analysis reveals the dominant presence of sulfur dioxide, ejected by constant eruptions. Lava flows sometimes reach more than 1,200 degrees Celsius, or 2,192 degrees Fahrenheit, which surprises researchers. Before Voyager, no one imagined that a body the size of Earth's moon could host so many volcanoes. This demonstrates a significant internal heat source maintained by gravitational tidal effects. In quick succession, researchers discover that Europa, another moon of Jupiter, presents a very different landscape. In the first high-resolution images, its surface appears relatively smooth, crisscrossed by long, straight fissures. Some lines evoke complex geometric patterns, suggesting the possible presence of an underground liquid ocean. Scientists immediately become passionate about the implications of this discovery. If a vast reservoir of water exists beneath the icy crust, Europa could potentially offer favorable conditions for life. At the time, this hypothesis was revolutionary and sparked immense enthusiasm in the community. However, exploration by Voyager does not stop at Io and Europa. Photographs reveal a faint ring around Jupiter, similar in principle to those of Saturn, albeit much less visible. Hints of such a ring had been suggested, but this direct confirmation amazes the scientific community. Simultaneously, Voyager's instruments detect two additional small moons, Adrastea and Thebe, in close orbit to the ring. Their small size and proximity to the planet suggest they contribute to maintaining this belt of debris by ejecting particles from their surfaces. The color images obtained by Voyager 1 and Voyager 2 permanently transform our perception of Jupiter. These images go beyond mere visual curiosity. They reveal a complex planet marked by alternating wind systems and gigantic whirlpools. To understand their origins, astronomers analyze temperature contrasts recorded on the different cloud bands. They discover that the gas giant emits more heat than it receives from the sun, a sign of internal energy production. It is thought that a slow process of gravitational contraction associated with internal differentiation phenomena explains this residual heat. As they pass, the two probes make infrared measurements of crucial importance. By scanning the giant planet in these wavelengths, they detect temperature variations between equatorial regions and the poles, providing insight into convective movements. Infrared study also reveals the chemical composition of the upper clouds, dominated by molecular hydrogen and helium with traces of methane and ammonia. Scientists understand that the planet has an internal thermal power that animates its atmosphere, an essential factor in explaining the genesis of extreme weather phenomena like the Great Red Spot. Voyager 2, which flies by Jupiter a few months after its sister, confirms most of these observations and adds new ones. Ground teams compare the readings of the two probes to study the stability of atmospheric patterns and the evolution of Io's volcanoes. Cross-analysis refines internal heat maps, thanks to more precise infrared readings. Meanwhile, careful observation of the outer moons reveals that the Jovian system is populated with many small bodies, some of which remain unknown. Astronomers already glimpse the impressive complexity of this planetary region. Later, the detailed analysis of the color images offers an almost artistic view of Jupiter's atmosphere. The brown and beige bands, punctuated by white ovals, seem to dance around the Great Red Spot, a gigantic anticyclone active for several centuries. The probes also reveal the existence of smaller vortices, which appear and disappear within a few days. This rapid dynamic demonstrates how turbulent the Jovian atmosphere is. In trying to model these phenomena, planetary scientists mention a mechanism similar to that of terrestrial hurricanes, amplified by Jupiter's ultra-fast rotation, completing a rotation on itself in less than 10 hours. Beyond these spectacular images, the instruments measuring charged particles, magnetic fields, and plasma significantly enrich the scientific aspect. The probes confirm that Jupiter's magnetosphere extends for millions of kilometers, or miles, forming a gigantic protective shield. This structure traps numerous ionized particles, generating powerful auroras around the planet's poles. For the first time, humanity accesses in situ data on how a gas giant interacts with the solar wind. This information will later help to better understand phenomena observed around other giant planets. At the end of their flyby, Voyager 1 and Voyager 2 continue their journey towards Saturn, carrying with them a treasure trove of data. Scientists will spend several years analyzing the pictures, spectra, and magnetic readings collected. Nevertheless, the main results are quickly shared with the general public, and the importance of this campaign for understanding the Jovian world becomes clear. The color images, in particular, resonate widely in the media because they reveal for the first time the nuances of Jupiter's atmosphere and the geological diversity of Io and Europa. These discoveries show that even the satellites of this imposing planet can harbor remarkable singularities, already inspiring robotic exploration projects. Between the early 1990s and the middle of the same decade, Jupiter became the setting for spectacular events that marked both the scientific community and the public. At the heart of this period, two major episodes captured the attention of all planetary astronomy: the dramatic impact of the Shoemaker-Levy 9 comet fragments on the gas giant, and the triumphant arrival of the Galileo probe in orbit around Jupiter. To understand the magnitude of these discoveries, it is essential to trace the context and measure the lasting influence they have had on our vision of the solar system. The Shoemaker-Levy 9 comet was first spotted in March 1993 by astronomers Carolyn and Eugene Shoemaker, along with David Levy. From the first observations, it appeared that the comet was broken into multiple fragments. This disintegration was due to Jupiter's intense gravitational field, which had recently captured the celestial body. The tidal forces, resulting from the difference in attraction between the close and distant parts of the comet, gradually split Shoemaker-Levy 9 into about 20 distinct pieces. Astronomers assigned them letters from A to W to precisely track their trajectory in the months preceding the collision. According to forecasts, these fragments were expected to collide with Jupiter's upper atmosphere in July 1994. Each traveled at nearly 60 kilometers, or 37 miles per second, or more than 200,000 kilometers, or 124,274 miles per hour. Terrestrial and space telescopes were mobilized to observe the impact, an unprecedented opportunity to witness a fragmented celestial body meeting a giant planet live. As July approached, excitement grew among scientists, eager to see how the Jovian shield, known for deflecting or absorbing many cosmic objects, would respond to these successive bombardments. In July 1994, the spectacle lived up to all its promises. For several days, fragments penetrated Jupiter's atmosphere, heating up as they passed through. Titanic explosions released immense amounts of energy, generating colossal plumes rising more than 3,000 kilometers, or 1,864 miles above the clouds. From Earth, dark spots appeared on the visible surface of the planet, where the atmosphere had been shaken and burned by the impact. These marks, compared to scars, persisted for several months, offering astronomers a valuable opportunity to study the movements and chemical composition of Jupiter's cloud layers. Scientifically, this event allowed for a better understanding of how a planet mainly composed of hydrogen and helium responds to the arrival of external matter. Spectral analyses highlighted a richness in gases such as sulfur and its derivatives, proving that the collisions brought up deep-seated elements. Researchers could study wind dynamics, the vertical and horizontal distribution of certain gases, and measure the propagation of disturbances in the Jovian atmosphere. Additionally, this series of collisions confirmed the protective role that Jupiter plays for the inner planets, particularly Earth, by intercepting numerous wandering objects. While Shoemaker-Levy 9 captured worldwide attention, another decisive mission was on its way to Jupiter, the Galileo probe. Launched in October 1989 by the Jet Propulsion Laboratory, its mission was to study Jupiter and its moons over a long period. Its journey across the solar system, punctuated by gravitational assists around Venus and Earth, lasted nearly 6 years. One of the major objectives relied on a descent probe, intended to penetrate Jupiter's atmosphere to collect direct data, a first in Jovian exploration. This probe was equipped with a heat shield designed to withstand temperatures of several thousand degrees Celsius or several thousand degrees Fahrenheit during atmospheric entry. Lacking a solid surface, Jupiter offered no landing point. the probe had to plunge until the extreme pressures and temperatures ended its mission. On Earth, atmospheric pressure at sea level is about 1 bar. Inside Jupiter, it increases rapidly from the first cloud layers. Engineers designed a module capable of recording measurements as it descended through these gaseous strata. In December 1995, Galileo reached Jupiter and released the descent probe. It traversed the upper layers of the atmosphere, where powerful winds already blow and meteorological phenomena of rare intensity occur. Friction and compression subjected the shield to extreme temperatures. Despite these conditions, the probe transmitted crucial data on gas composition, atmospheric structure, and wind speed to the orbiter, then to Earth. As it progressed deeper, it detected molecules such as ammonia and methane, revealing the complexity of Jovian meteorology. The probe eventually succumbed to a pressure of about 0.5 bars, or 0.5 atmospheres, which is half that measured at sea level on Earth. This level, although relatively shallow for Jupiter, already represented an extremely hostile environment. The temperature was significantly higher than in the upper layers, and the atmospheric density increased sharply. The readings raised new questions about the distribution of water, as the probe detected a lower vapor content than expected. This result fueled scientific debates, with some suggesting the probe passed through a dry region, while others hypothesized internal mechanisms hiding water at these depths. During this time, the Galileo orbiter settled into orbit around Jupiter. Designed to withstand the intense radiation of the Jovian system, it was equipped with a variety of instruments, including a wide-angle camera, an infrared spectrometer, and a particle detector. From the very first orbits, it was able to closely observe the typical cloud bands of Jupiter, those light and dark zones where supersonic winds cross paths. It also explored the magnetic field, far more powerful than Earth's, and analyzed the distribution of energetic particles in the magnetosphere. The Galileo mission established itself as the most ambitious ever conducted around Jupiter, offering a comprehensive understanding of a planet previously only flown over. The convergence of these two events, the collision of Shoemaker-Levy 9 and the arrival of Galileo, revolutionized the perception of Jupiter. On one hand, the impact of the comet illustrated the guardian role that Jupiter can play for the inner planets, while providing a unique opportunity to observe its atmosphere under the effect of massive collisions. On the other hand, Galileo allowed for the first time a prolonged and detailed study of the structure, composition, and dynamics of the planet, both from orbit and from within its atmosphere. These data challenged some hypotheses on the distribution of gases and confirmed several models on the formation of giant planets. The information transmitted by Galileo was cross-referenced with the observations of telescopes that monitored the impact of the Shoemaker-Levy 9 fragments. The giant plumes revealed how Jupiter's internal circulation could disperse or concentrate materials coming from outside. By comparing the chemical signatures with the temperature readings obtained on site, researchers refined their understanding of heat propagation under the clouds. The measurements from the descent probe, combined with the orbiter's images and spectra, unveiled a world far more dynamic and complex than previously imagined. The idea that Jupiter has played over time the role of a gravitational shield for the inner solar system has been reinforced. Following these events, researchers refined their theories on the formation and evolution of giant planets. Galileo transmitted an impressive amount of data illuminating Jupiter's internal chemistry, while Shoemaker-Levy 9 highlighted the crucial role of collisions in the architecture of the solar system. Together, the comet and the probe revealed that Jupiter is a true cosmic laboratory, conducive to studying extreme meteorology, fluid dynamics in an atmosphere without a solid surface, and the power of giant magnetic fields. Thus, between 1990 and 1996, the universe offered us a striking glimpse of the largest planet in the solar system. In a short time, Jupiter revealed itself in spectacular and unexpected ways, a shield against threatening celestial objects, but also a vibrant world where physical and chemical phenomena unfold on titanic scales. This period remains etched in the history of space exploration, not only for the fascination it inspired, but especially for the decisive impetus it gave to our understanding of gas giants, and by extension, to Earth's place in the grand cosmic narrative. From 1996 to 2003, the Galileo probe spent 7 full years in orbit around Jupiter. It was a first. Never had a mission stayed so long in the Jovian environment. The discoveries made during this time profoundly transformed our vision of these distant worlds. Let us therefore prepare to relive this journey around Jupiter through observation missions, onboard instruments, and the knowledge science has gathered, step by step, until Galileo's final plunge into the atmosphere in 2003. To measure the scope of this adventure, Galileo must first be placed in its context. After a long journey through interplanetary space, the probe arrived near Jupiter at the end of 1995. The true beginning of its scientific mission occurred in the first half of 1996, when the orbiter began the first of its many elliptical loops around the giant planet. Each orbit was designed to fly over specific moons or explore different zones of the magnetosphere, offering Galileo the opportunity to collect precise data on the composition, temperature, and dynamics of these extreme environments. From the very first months, the images and readings transmitted proved that the exploration of Jupiter was just beginning. The success of this mission depended largely on the design of the onboard instruments. Galileo was equipped with a camera capable of producing highly detailed images of lunar surfaces in Jupiter's upper atmosphere. It also carried a spectrometer that measured light at different wavelengths to identify the composition of observed materials. A magnetometer was used to detect variations in the magnetic field, while a particle detector tracked the flow of ions and electrons around the planet. Other sensors measured temperature and pressure near Jupiter and its moons. This array of instruments covered a wide range of physical phenomena, from geological to electromagnetic. In 1996, no one suspected that Jupiter's moons held such secrets. Orbit after orbit, Galileo performed targeted flybys, Io for its volcanoes, Ganymede for its icy structures, Callisto for its craters, and Europa, which was already under scrutiny. From Earth, some clues suggested that a liquid ocean might be hiding beneath Europa's ice. This hypothesis was based on the reflectivity of the surface and the presence of cracks and ridges. Engineers then planned the flyby of Europa to obtain much more precise data than previously available. By skimming the surface of Europa, Galileo detected clues pointing to a salty ocean hidden beneath the ice layer. It measured disturbances in Jupiter's magnetic field near the moon. If Europa had been a solid block of ice, no notable changes would have been recorded. However, the detected variations indicated the presence of electric currents induced in a salty layer, likely liquid water with dissolved salts. This discovery changed the perception of a habitable ocean on a frozen moon, from speculation to a serious hypothesis. It captured the scientific imagination, broadening our perception of potentially habitable places in the solar system. the same time, Galileo turned its attention to Ganymede, the largest moon in the solar system, even larger than Mercury. Its surface was a mix of ancient terrains and brighter areas, indicating past activity. Thanks to its measurements, the probe confirmed that Ganymede generates its own magnetic field. This internal dynamo, similar to Earth's, reveals an active core. This discovery raised new questions about the possibility that other moons or certain exoplanets might also have internal magnetic fields. While observing the moons, Galileo did not neglect Jupiter itself. The planet is distinguished by its colorful bands, its brown, orange, and white hues, and its colossal storms. Among them, the Great Red Spot, a famous anticyclone visible since the 17th century, was the subject of multiple studies. Temperature measurements taken by Galileo revealed that it was about 20 degrees Celsius, 36 degrees Fahrenheit, warmer than its immediate surroundings. This difference provided valuable clues about the heat transfer mechanisms inside Jupiter. In addition to the Great Red Spot, Galileo observed Jupiter's polar auroras. These result from the interaction between Jupiter's magnetic field and the solar wind. They appear as luminous arcs near the poles, captured in ultraviolet or infrared. Even though detailed study of them continued long after, Galileo provided the first data on particles precipitating into the atmosphere. These observations allowed for a more complete picture of the energy transfers between Jupiter, its moons, and the solar wind. Another achievement of the mission lies in the study of Io, the closest moon to Jupiter among the major Galilean moons. Io presents unmatched volcanic activity throughout the solar system. Some eruptions eject plumes of gas and sulfur to dizzying heights. Even before the 2000s, Galileo had already captured spectacular images of these phenomena. Its thermal recordings made it possible to map the extent of lava flows and measure the extreme temperatures reached on the surface. These data, although less covered in the media, were essential to understanding how Io releases its internal energy and how Jupiter's gravitational influence fuels this relentless geological activity. Between 1996 and 2003, Galileo multiplied its flybys of moons, refined our understanding of the Jovian magnetic field, and reinforced the idea that Jupiter harbors fascinating environments for the search for life. But over time, the spacecraft showed signs of wear. The intense radiation around the planet gradually damaged its systems, while the reserves of propellant necessary for maneuvers were depleting. The engineers knew that the end of the mission was approaching, and they had to organize an end that was both secure and scientifically relevant. One of the major constraints was to avoid any biological contamination of Jupiter's moons. Despite precautions taken before launch, it was possible that Earth microbes had survived. If Galileo continued its drift, an accidental impact on a moon like Europa would have compromised future research. To prevent this risk, NASA planned a controlled plunge into Jupiter's atmosphere, set for 2003. The chosen trajectory ensured that the spacecraft would disintegrate before reaching the deep layers, without threatening the natural satellites. During this final descent, Galileo continued to transmit data until the pressure of the atmosphere completely crushed it. The ground teams collected every piece of information on the composition of gases, temperature, and parameters encountered. Even in its final moments, the spacecraft enriched our knowledge of Jupiter. Then, in September 2003, it burned up, concluding 7 years of invaluable observations. The end of the mission sparked strong emotions among those who had followed Galileo from its inception. Launched from the Space Shuttle Atlantis in 1989, it had completed a long gravitational journey before reaching Jupiter. But it was between 1996 and 2003 that it made most of its discoveries. During this period, the study of the moons transitioned from a mere astronomical interest to a major scientific challenge, revealing buried oceans, studying magnetic fields, observing active volcanoes, and understanding the workings of Jovian storms. With the mission's end, a cycle came to a close. Other means have taken over to continue exploration, from Earth or via other probes. But Galileo proved that a prolonged stay on site could transform our view of the giant planet. Even today, the data collected between 1996 and 2003 remain crucial. Scientists continue to analyze them, especially the variations of fields and particles, to refine comparisons with measurements from more recent missions. One of Galileo's great lessons is that a long, varied orbit with context-rich measurements provides a much richer understanding than a simple flyby. In 2003, the final descent saw the spacecraft compressed, then pulverized by Jupiter's atmosphere, reaching extreme temperatures of several thousands of degrees Fahrenheit. This thoughtfully considered sacrifice was aimed at avoiding biological pollution. But beyond this precaution, the gesture carried a symbol. Galileo, which had revealed so much about Jupiter, disappeared into it as a final tribute to the planet it had explored so intimately. Thus concluded the story of these 7 years in orbit, from 1996 to 2003, a major chapter of space exploration. Among its most significant contributions, the likelihood of an ocean beneath Europa's surface, the discovery of Ganymede's own magnetic field, the detailed analysis of the Great Red Spot, and the study of Io's volcanoes. These revelations have paved the way for new scientific questions. This legacy has inspired a new generation of astronomers, engineers, and exobiologists, all motivated to continue studying these icy and dynamic worlds. In September 2003, one thing was certain: human curiosity would eventually drive us to return to probe Jupiter and its moons. For 7 years, Galileo had written one of the most beautiful chapters of space exploration, filled with discoveries and wonders, a narrative where water, ice, and fire coexist around a giant world. And this adventure, even today, inspires future missions, new observations, and research on the fringes of our solar system. Galileo's journey was brief on the scale of the universe, but its legacy remains invaluable. Between two major stages of Jovian exploration, the first decade of the 21st century saw 2 key missions: the Cassini probe in 2000, followed by New Horizons in 2007. Both inaugurated the era of rapid flybys, these close passes designed to capture a maximum of information without entering orbit. During these missions, images of unprecedented precision unveiled surprising details about Jupiter's atmosphere and its still little-known ring system. They also highlighted the effectiveness of gravitational assist maneuvers, which allow probes to accelerate while collecting valuable data. To understand Cassini's 2000 flyby, it's important to remember that its final destination was Saturn. To reach it without consuming too much fuel, the probe had to perform several gravity assist maneuvers. This technique involves approaching a planet to use its gravity as a slingshot. The flyby of Jupiter thus allowed for trajectory correction towards Saturn, while offering a unique opportunity to observe the gas giant. The mission team knew that Cassini had exceptionally high-quality sensors, capable of revealing the finest details of the Jovian system. During this passage, the focus was on Jupiter's upper atmosphere, an extreme domain where powerful winds, swirling clouds, and gigantic storms prevail. This upper region, where the pressure remains low but the activity intense, is primarily composed of hydrogen and helium, with traces of methane and ammonia. Thanks to its high-resolution camera, Cassini captured fascinating images of these colorful clouds, punctuated by fine and transient structures. Shades ranging from white to brown reveal the chemical richness of these atmospheric layers. Complex photochemical processes, activated by sunlight and internal electricity, partly explain this palette of hues. The phenomenon of lightning drew particular attention because it offers a window into the violent weather that shakes Jupiter's atmosphere. On Earth, they originate in storm clouds where ice and water interact, causing a separation of electrical charges. On Jupiter, the mechanism is comparable but on a gigantic scale, within clouds that can extend over several thousand kilometers or miles. Cassini's sensors, sensitive to visible and infrared light, detected flashes of remarkable intensity, attesting to the presence of powerful storms. Measurements revealed that these lightning strikes sometimes release energies hundreds of times greater than those observed on our planet. This phenomenon reflects an intense convection cycle. The internal heat, combined with gas movements, leads to the ascent of electrically charged masses of matter before they descend into the deeper layers. Beyond the storms, Cassini captured variations in brightness at high altitudes. Its spectrometer, capable of analyzing light according to different wavelengths, identified the characteristic signatures of gases like ammonia, water, methane, or ammonium hydrosulfide. These readings refined the understanding of the complex chemistry inside and around Jupiter's cloud formations. The data were then cross-referenced with observations made from Earth's orbit to isolate the role of each component. This rigorous work enabled the creation of a chemical map of unprecedented precision. After this fruitful flyby, Cassini continued its journey to Saturn, leaving behind a wealth of exciting data. Although it only passed by, this phase demonstrated the effectiveness of close flybys for gathering crucial information about distant planets. A few years later, in 2007, a new mission followed the same path, with a more distant objective, the New Horizons probe en route to Pluto and the Kuiper Belt, where the solar system fades into interstellar space. Before heading to these icy regions, it flew by Jupiter to benefit from a gravitational boost, but also to conduct a series of unprecedented observations. At the beginning of the year 2007, New Horizons arrived near Jupiter and activated its instruments to map the inner rings and several moons. These rings had already been spotted by the Voyager probes in the 1970s, but the precision of New Horizons cameras provided a much more detailed view. Unlike Saturn's bright, ice-rich rings, Jupiter's rings appear dark and scattered. They are often described as tenuous because they are primarily composed of dust from micrometeorite impacts on the moons close to the planet. The analysis of light scattering revealed that these particles vary in size, ranging from a few microns to several hundred. These measurements have greatly enriched our understanding of ring renewal through the constant erosion of satellites. A major discovery by New Horizons was the presence of density waves in the rings. This phenomenon manifests as alternating dense and less dense zones, akin to waves. These undulations can result from gravitational interactions with the satellites or with the planet itself. The probe observed bright concentric patterns, suggesting a regular variation in the distribution of particles. These structures, already known in Saturn's rings, were identified for the first time on those of Jupiter with such clarity. For scientists, these waves reveal how the gravitational field, rotation, and effects of the moons influence the arrangement of the dust. Their study allows scientists to deduce the mass, resonances, and distribution of surrounding bodies. During this passage, New Horizons also filmed the Jovian atmosphere in search of storms. This hunt for rapid phenomena, such as cyclonic eruptions or storm surges, is essential to decipher the planet's constant dynamics. The data confirmed the existence, already detected by Cassini, of vast storm systems evolving in a few days. The images showed impressive details in the dark and light bands encircling the planet, where winds can exceed several hundred kilometers or miles per hour. Fleeting flickers in these bands revealed the presence of lightning, indicating that the storms extended into the deep layers. The probe then used Jupiter's gravity to accelerate and continue its journey to the edges of the solar system. Before disappearing into the outer regions, the collected data were meticulously analyzed by several teams on the ground. Researchers studied the precise distribution of dust in the rings in relation to the influence of the moon Métis and the satellite Adrastea, both located within this zone. The measurements of brightness and diffraction of light reinforced the idea of a very active system, fueled by multiple impacts. This fluctuating activity, still not well understood, was illuminated by the discovery of density waves, opening new approaches to the internal structure of the rings. To put these results in context, it is important to remember that Jupiter is a giant whose diameter is 11 times that of Earth. Its gravity and rapid rotation cause intense convective movements. All of its rings are constantly subjected to the effect of multiple forces. Before the images from New Horizons, these structures were believed to be relatively stable. The 2007 surveys revealed a much more dynamic and fragmented system, marked by frequent collisions. The mapping highlighted arcs of denser material, indicating the possible presence of aggregates or fragments detached from nearby moons. On the thermal front, New Horizons conducted surveys using an instrument measuring infrared emissions. Although not specialized for probing deep temperatures, it allowed for evaluating the heat distribution in the upper layers. This distribution varies greatly, dropping to 120 degrees or 184 degrees Celsius in some high clouds, and rising to 70 or 94 degrees Celsius or 80 degrees Celsius or 112 degrees Celsius in warmer areas. These surprisingly high values at this distance from the Sun are explained largely by the planet's internal heat. It is this energy that powers the convective movements and vast storms. Between 2000 and 2011, Jupiter received two visits that were as brief as they were intense. The first, by Cassini, captured stunning images of the storms and confirmed the chemical diversity of the clouds. The second, by New Horizons, pushed the boundaries of our understanding of the rings. Thanks to a detailed mapping, the probe revealed the presence of density waves, clues to gravitational and collisional activity far more complex than expected. Each time, the challenge was to collect a maximum amount of information in a very limited time. These flybys sometimes last only a few days, but the discoveries they allowed have left a considerable scientific legacy. The engineers and scientists of the Cassini and New Horizons missions took advantage of their observations to refine their understanding of the internal workings of the gas giant. In parallel, these results enabled the design of more sophisticated instruments, capable of precisely targeting atmospheric phenomena and detecting the slightest variations in the density or composition of the rings. This approach, based on the optimization and complementarity of successive flybys, has profoundly influenced our way of approaching planetary exploration. Cassini and New Horizons spent only a short time near Jupiter, but the quality of their data reveals a constantly evolving planet, animated by powerful storms and turmoil among the dusty rings. They have thus proven that a well-prepared quick passage supported by cutting-edge technology, can become a major scientific event. For the general public, the images sent back by these probes have sparked lasting wonder. They revealed the fascinating beauty of swirling clouds, the spectacular scale of the Great Red Spot, and the delicate finesse of the dust-formed rings. These moments stolen at high speed reminded everyone that Jupiter is a living, restless planet, and that a simple glance can be enough to unveil a striking panorama of its activity. The period from 2000 to 2011 can thus be described as the era of rapid flybys, where the coordination between engineers, scientists, and planners revealed all the richness that a short interplanetary passage could offer. The combined results of Cassini and New Horizons highlighted Jupiter's underestimated potential when observed with recent instruments. Thanks to their remote sensing tools, the probes collected key data on the structure of the rings, the nature of the storms, and the dynamics of the clouds. Researchers understood that, despite the complexity of this immense planet, the variety of study angles, depending on seasons and latitudes, allowed for the reconstitution of an increasingly detailed puzzle. This puzzle constantly evolves. Over time, changes are observed in the atmosphere, the intensity of storms, and the activity of the inner moons, all interacting with the rings. Without the 2000 flyby, Cassini could not have validated certain instruments before its main mission around Saturn. And without the 2007 flyby, New Horizons would not have produced such a fine study of the density and organization of the rings, establishing a valuable point of comparison with those of Saturn. These discoveries also played a decisive role in the preparation of future missions to Jupiter and its moons, revealing the immense diversity of this planetary system. Even if these programs were not a priority at the time, the mass of information collected at this pivotal moment paved the way for projects dedicated to the icy satellites, magnetic fields, and internal energy sources of the planet. Cassini and New Horizons thus showed that a simple passage can, between two major orbital missions, produce decisive revelations. These two flybys, brief as they were, demonstrated that planetary exploration relies above all on the precision of the instruments, the intelligence of the trajectories, and rigorous planning. Thanks to these efforts, we now know that Jupiter, massive and swirling, still hides many enigmas in its storms and rings, and that a simple, well-orchestrated approach can reveal an unsuspected part of it. Between two major milestones in space exploration, between 2011 and 2016, a new mission named Juno came to life. Designed to meet one of the major challenges of the American Space Agency, its goal was to reach Jupiter, located about 740 million kilometers, or 460 million miles, from the Sun, to study its composition, magnetic field, and atmospheric dynamics. The name of the probe echoes Roman mythology. Juno, the wife of Jupiter, is able to see through the clouds deployed by her husband to hide his secrets. This symbolism perfectly illustrates the scientific mission entrusted to Juno, to uncover the mysteries hidden beneath the thick cloud cover of the planet. The preparation for this adventure began in the early 2000s, but it was on August 5, 2011, that the mission truly took off. On that day, from Cape Canaveral in Florida, the Atlas V rocket launched amidst a blaze of flames and power. The team had meticulously defined the trajectory of the probe, which was to undertake a long journey of nearly 5 years. Just after separation from the launcher, Juno deployed its solar panels, essential for providing the energy needed throughout its journey and in orbit around Jupiter. Unlike other missions that rely on nuclear generators, Juno uses large solar wings, requiring constant orientation to capture sunlight as effectively as possible, despite the considerable distance. Once on the way, the probe made several trajectory adjustments through the inner solar system. One of the key moments of its journey was the Earth flyby. In October 2013, after more than 2 years of travel, Juno passed close to our planet to take advantage of its gravitational force and accelerate. This process, which consists of using Earth's gravity to increase speed without consuming too much fuel, allowed the probe to continue its journey to Jupiter more efficiently while preserving its resources. The journey to the giant planet was not without difficulties. Ground teams closely monitored every signal from the probe, ensuring that the electronics could withstand cosmic radiation and extreme temperature variations. Even though Juno had not yet entered Jupiter's formidable radiation belt, it was already enduring harsh conditions between intense cold when moving away from the sun and temperature rises during certain course corrections. In all circumstances, engineers ensured the instruments on board were functioning properly. As it approached its target, tension mounted. Researchers were preparing to probe the depths of Jupiter to determine if the planet has a solid core, accurately measure its magnetic field, map its gravitational field, analyze the cyclones present at the poles, and track the evolution of its dense clouds. To do this, Juno was equipped with a series of advanced instruments. 3 of them were to play a crucial role from the moment it entered orbit: GIRAM, MWR, and MAG, each dedicated to a specific area of exploration. Let's begin with GIRAM, an acronym for Jovian Infrared Auroral Mapper. It is an infrared observation system designed to study Jupiter's polar auroras. In these regions, powerful interactions between the planet's magnetic field and solar particles generate striking luminous phenomena comparable to terrestrial auroras, but on a gigantic scale. GIRAM detects the infrared emissions generated by these auroras and provides precise data on their composition, distribution, and intensity. This approach helps to better understand how the upper atmosphere reacts to the arrival of energetic particles and how energy propagates to deeper layers. The second instrument, MWR, or microwave radiometer, allows the exploration of the planet's internal atmospheric layers down to about 3,000 kilometers, or 1,464 miles, below the visible clouds. Its principle is ingenious. It captures how Jupiter's thermal emissions pass through different frequency bands. By measuring their intensity, it is possible to estimate the temperature and depth, analyze the gas composition, and track the dynamics of internal currents. Each atmospheric layer emits a particular signal, and MWR acts as a receiver that captures them. By studying absorption and re-emission, a detailed profile of the planet's interior is obtained, much like a scanner reveals the internal structures of a human body. The third essential instrument, MAG, is a magnetometer that measures the intensity and orientation of the magnetic field. It consists of 2 sensors placed at the end of a boom to eliminate interference from the spacecraft. Thanks to these measurements, it is possible to accurately map the lines of force surrounding Jupiter. The objective is to understand the shape of the field, identify regional anomalies related to the movements of conductive materials inside, and analyze its interaction with the solar wind. The stakes are high because Jupiter's magnetosphere is the largest in the solar system, extending millions of kilometers or miles in periods of solar calm. The rendezvous with Jupiter was set for the early days of July 2016, a significant date for space research. When Juno approached sufficiently, The crucial phase of orbital insertion began on the night of July 4th to 5, Universal Time. The main engine had to be ignited for about 30 minutes to slow down the spacecraft and have it captured by the planet's gravity. A delicate operation. In case of engine failure or communication cutoff, the spacecraft would have continued on its path into space, negating years of preparation. In the control room, every parameter was scrutinized with extreme attention. Everything went as planned. The engine ignited, using the fuel reserved for this critical maneuver. Less than an hour later, Juno was in orbit around Jupiter. It was following a polar trajectory, flying over the north and south poles successively. This strategy partially avoided the most intense radiation zones located near the equator. Thus, the spacecraft began its first loop, lasting approximately 53 days. During each pass, it approached the planet at its closest, at the perigee, skimming the clouds at an altitude of around 4,100 kilometers or 20,248 miles, a remarkable proximity given Jupiter's size. This choice of a 53-day-long orbit was a compromise between scientific efficiency and preservation of the spacecraft. A shorter 14-day orbit had been considered, but the constraints of the propulsion system and the intensity of the radiation led to the preference for a wider trajectory. Each perigee offered an optimal moment to activate the instruments and gather high-precision observations before moving to a less exposed zone. During each flyby, Jiram observed the auroras at the poles, capturing the luminous arcs and the distribution of hydrogen in the upper layers. Meanwhile, MWR recorded internal emissions, enabling the tracking of ammonia, water, and other compounds in different layers. These recordings helped model the circulation of internal heat, revealing that Jupiter produces more energy than it receives. Meanwhile, MAG revealed the complexity of the magnetic field. The first data showed unexpected variations, suggesting that internal layers were in motion. These analyses refined our understanding of the transition between molecular hydrogen and its metallic state, which conducts electricity. A major challenge was to protect the onboard computer and sensors from the energetic particles present in Jupiter's environment. For this, sensitive components were enclosed in a titanium-shielded box nicknamed the Vault. This shielding reduced the impact of the particles, but the gradual accumulation of exposure of the spacecraft would eventually degrade it. Engineers were aware of this and had anticipated this wear to maximize scientific return before it became critical. The successful insertion on July 5, 2016, marked the beginning of a highly anticipated exploration phase. Each meeting at the control center became an opportunity to analyze the data. The thermal readings from MWR, the magnetic maps produced by MAG, the polar infrared images from JIRAM, and pictures from the onboard camera intended for the general public. The first discoveries highlighted cyclones at the poles, differing in structure from those observed on Earth, as well as high-altitude clouds. Indications also suggested that Jupiter's core might be less dense or partially dissolved in its inner envelope. NASA highlighted that the Juno mission went far beyond merely collecting impressive images. It aimed to validate or challenge theories about the formation of the solar system. Jupiter, due to its mass, accumulated the gases and dust present from the early days of the primordial nebula. Studying its internal composition is like tracing back the thread of our cosmic origins. Exploring what lies beneath its clouds is key to understanding the processes that have shaped planets, including our own. From 2011 to 2016, Juno's journey to Jupiter's polar orbit was an achievement. From launch to Earth gravity assists, and finally orbital insertion, each step demonstrated the precision, robustness, and inventiveness required for such a mission. The arrival of the probe in Jupiter's immediate environment was a pivotal moment. The first data immediately sparked worldwide excitement, revealing unprecedented structures and confirming the vastness of what remains to be discovered. The choice of a 53-day polar orbit also helped preserve the probe from the most harmful radiation. Each flyby provided a new perspective on the cloud-covered surface, allowing the GYRAM, MWR, and MAG instruments to collect complementary information. Together, these sensors offered a complete picture, linking atmospheric observations to unseen internal structures. But the polar orbit was only one of many challenges. The probe's lifespan was limited by the intensity of Jupiter's radiation field, one of the most formidable in the solar system. Each orbit was, therefore, precious. It was necessary to continuously adjust the probe's orientation to ensure reliable measurements and transmission back to Earth. This mission showed that exploring gas giants requires both boldness, rigor, and resilience. Ultimately, the period from 2011 to 2016 symbolizes Juno's rise to power. Its heroic journey from Florida soil to Jupiter's orbit crowned years of design, testing, and simulations. The data from this mission would challenge or consolidate our ideas on planet formation, refine the mapping of gravitational and magnetic fields, and open new avenues for understanding why Jupiter, despite its gigantism, still retains so many mysteries. The successful orbit insertion on July 5, 2016, at just 4,100 kilometers, or 2,548 miles, above the clouds during Perihove, marked the true beginning of investigations. From that point on, for each 50-day orbit, Juno observed Jupiter like a methodical explorer. JWST captured every infrared glint, identified hotter areas, revealed shifting auroras, and measured the presence of molecules like hydrogen or methane. MWR delved into the gaseous depths, tracked ammonia and water, mapped thermal gradients by latitude, and detected atmospheric nuances below the surface. Meanwhile, MAG recorded the slightest variations in the magnetic field, identifying gradients or anomalies related to deep movements, such as electric currents induced by the rapid rotation. Remember that Jupiter rotates on its axis in less than 10 hours, generating a remarkable dynamo effect. This foundational work, initiated as soon as orbit was reached, laid the groundwork for a new era of discoveries during this initial phase. The scientific team's dedication was evident in the attention given to instrument settings, repeated calibrations, and fine-tuning methods to ensure maximum reliability. The raw data collected required months, sometimes years, of interpretation to extract solid conclusions. Behind each measured parameter, every infrared spectrum or magnetic reading, lies a story about how Jupiter formed, evolves, and interacts with its spatial environment. Viewed from Earth, Jupiter appears as an immense disk streaked with colorful bands. Thanks to Juno, scientists have been able to delve into these bands down to the zones where storms and swirling structures originate. The investigation focused on the internal states of hydrogen, helium, and other gases, the presence of heavier elements, and potential transitional layers between different pressures. The instruments GYRAM, MWR, and MAG were precisely designed to address these major questions. Together, they form the scientific core of the mission, a synergistic trio capable of analyzing Jupiter from the high atmosphere down to several thousand kilometers, miles, deep. Thus, the period from 2011 to July 5, 2016, represents the success of an exceptional launch and arrival. Juno demonstrated technological performance in reaching Jupiter with a clear objective: to establish a polar orbit of 53 days, skim the planet at 4,100 kilometers, approximately 2,548 miles, from the cloud layer, and activate a set of sophisticated instruments without succumbing to radiation was an achievement. This feat opened an unprecedented window into Jupiter's invisible interior, promising a wealth of discoveries and a new perspective on the largest planet in the solar system. Such is the challenge of this sequence, titled 2011-2016, Launch and Polar Orbit Insertion of Juno. During these years, NASA made a decisive step in understanding the chemistry, physics, and deep structure of Jupiter. By combining the polar trajectory with the precision of the GIRAM, MWR, and MAGI instruments, Juno laid the foundations of a new era, where the giant with 100 faces begins to reveal its secrets. It is now possible to explore the planet's intimacy, to dive down to 3,000 kilometers, approximately 1,864 miles, beneath the clouds, and to map parameters previously inaccessible. By July 2016, the mission was only beginning, but it had already accomplished the essential, piercing the veils of Jupiter and offering scientists the chance to approach the heart of a cosmic enigma sealed for billions of years. In 2021, the astronomical community eagerly awaited the full operational launch of the James Webb Space Telescope, an international project designed to push the boundaries of space observation. After many years of development, this gigantic instrument, positioned in space at a stable point between Earth and the Sun, began collecting unprecedented data on a variety of celestial objects, including Jupiter. Its main objective was to leverage advanced technology to produce measurements and images in near-infrared, a range of wavelengths capable of effectively penetrating the cloud and haze layers of planets. Throughout 2021, the technical teams conducted a series of calibrations, tests, and adjustments to ensure all instruments functioned according to rigorous standards. During this initial phase, several research groups began designing a study program specifically targeting Jupiter, a gas giant with a complex atmosphere, whose wind dynamics, storms, and polar auroras arouse keen interest. These auroras, light displays at the poles, result from the impact of energetic particles on molecules in the upper layers of the atmosphere under the influence of solar wind and the planet's magnetic field. On Jupiter, they stand out for their intense brightness and magnitude, particularly at the north and south poles. From Earth, some telescopes sensitive to infrared or visible spectrum had already allowed their observation, but the distance and atmospheric turbulence greatly limited image quality. It is in this context that, in 2022, the James Webb Space Telescope turned its instruments toward Jupiter. The goal was to continue exploring the Jovian high atmosphere by focusing on the infrared signatures of gases and aerosols present in the various cloud layers. Among the instruments mobilized is the Near-Infrared Camera, or NIRCam, designed to capture near-infrared radiation. These wavelengths, broader than those of visible light, allow traversing the haze and detecting emissions related to magnetic and thermal phenomena. In August 2022, the telescope team released spectacular images of Jupiter. According to an official NASA blog, these views showed immense auroras extending around the planet's poles with unprecedented clarity. Near the North Pole, bright arcs marked the interaction between ionized particles and the magnetic field. In the southern hemisphere, luminous arabesques formed moving patterns on the periphery of the pole. These phenomena immediately caught the attention of the scientific community, which noted that they occurred in areas where ultraviolet or infrared radiation could be continuously monitored. In addition to these auroras, the James Webb Space Telescope images also revealed a high-altitude haze covering certain regions of Jupiter's atmosphere. These are fine particles resulting from complex chemical reactions in the upper layers. Exposed to solar radiation, gases like methane transform and form light-diffusing particles. On Jupiter, violent winds redistribute these elements, forming bands or veils. Thanks to the telescope's exceptional infrared sensitivity, astronomers were able to observe for the first time in detail the vertical and horizontal distribution of these hazes. They analyzed the light intensity of each image pixel by comparing it to atmospheric models to locate the densest layers and track their movements. Researchers also noticed that these hazes preferentially form above jet streams, areas of the atmosphere where winds reach very high speeds. Known on Earth, these currents are even more powerful on Jupiter due to its rapid rotation. In regions where this speed generates strong turbulence, the mixing of aerosols is more intense. By mapping the haze, the telescope has provided new data on the connection between high-altitude winds and atmospheric chemistry. Furthermore, the infrared images allowed for detecting temperature variations from one region to another, expressed in degrees Celsius, DGF, revealing that some hazy areas were warmer, suggesting an interaction between internal dynamics and solar radiation. During this same period, the Juno probe continued its close study of Jupiter. The interest in comparing Juno with the Space Telescope lies in the complementarity of their perspectives. In orbit around the planet, Juno performs close flybys at regular intervals. It is equipped with instruments capable of measuring the local magnetic field, ionic composition, hydrogen concentration, and other essential parameters for understanding the deep atmosphere. It also carries radio detectors and a receiver specialized in emissions from energetic particles in the magnetosphere, as well as a microwave radiometer that explores the internal structure and circulations down to several thousand kilometers, miles, deep. For its part, the Space Telescope, much farther away, offers an overview and can simultaneously map large areas of the planet in infrared. While Juno records details close to the clouds, the James Webb Space Telescope renders atmospheric structures and auroras on a global scale. By cross-referencing and merging their data, researchers can establish correspondences between local phenomena observed by Juno and the larger patterns revealed by the telescope. This collaboration, particularly active at the end of summer 2022, relies on the synchronization between Juno's surveys and the images taken by the NIRCam. Jupiter's deep storms have been analyzed through this dual approach. Juno records the electromagnetic fields and radio signals generated by lightning, while the telescope spots atmospheric disturbances in the upper layers by capturing the infrared light emitted or reflected by ascending gas columns. When electrical activity is detected by Juno in a storm, and the telescope simultaneously observes an intense bright area in the infrared, researchers can deduce a link between deep movements and visible effects in the upper atmosphere. A violent ascent of gas and charged particles, stemming from a storm beneath the clouds, can heat its environment and produce a luminous emission detectable from a distance. This data combination allows for an unprecedentedly precise analysis of Jovian storms. A key point of this correlation concerns the vortices, those giant whirlwinds which feed the jet streams and polar cyclones. Identified long ago, these cyclones are the result of rising gas masses loaded with heat and influenced by pressure gradients. Juno, by measuring on site the magnetic field and particle density, confirms the intensity of these movements. The telescope, meanwhile, captures the shape and extent of the clouds lifted by this dynamic. By crossing the data, scientists have observed that some cyclones draw their energy from unsuspected depths, forming stable spirals visible for several orbits. To capture these whirlwinds, the NIRCam explores Jupiter at various wavelengths, allowing it to penetrate more or less deeply into the atmosphere. This is equivalent to an invisible slice, where layers of gas and aerosols in upward or downward motion can be distinguished. The heat, identified by the infrared brightness, can be translated into degrees Celsius or Fahrenheit. A warmer, brighter region indicates compression or release of energy. These clues perfectly match the measurements from Juno, which records in real time the pressure and radio waves emitted by moving particles. Beyond meteorology, the collaboration between the James Webb Space Telescope and the Juno probe sheds light on the mechanisms behind the Jovian auroras. When solar winds or Jupiter's magnetic field direct charged particles towards the upper atmospheric layers, they collide with hydrogen and other gases. These collisions cause the emission of light in several wavelengths, ranging from the infrared to the ultraviolet. Juno measures the trajectory and density of these particles, while the telescope maps the bright regions in real time. This cross-observation has revealed that the position of the auroras varies depending on the orientation of the magnetic field and the intensity of the solar wind. In August 2022, a moderate increase in solar activity was recorded. Juno captured an increase in the flux of particles directed towards the planet, while the infrared images from James Webb revealed a marked strengthening of the auroras, concentrated on the poles. During this period, a temporary densification of high-altitude haze was also observed, probably caused by an excess of aerosols from the impacts between particles and gas. It is likely that some of the heat produced in these extreme zones then spreads to lower latitudes well beyond the polar regions. These results, collected between 2021 and 2022, have generated notable enthusiasm among scientists. They demonstrate the value of combining an orbiting probe with an observatory equipped with an overall view. The combined data enriches detailed models describing the evolution of clouds and the visible manifestations of Jupiter's internal energy. Researchers thus hope to better understand the interactions between auroras, massive hurricanes, haze distribution, and thermal variations that traverse the atmosphere. It is this synergy between local measurements and a global vision that today embodies the heart of the infrared renaissance, mentioned by many specialists to designate this turning point in the study of Jupiter. Thus, the period from August to December 2022 marks an essential milestone. The data still needs to be analyzed in depth to unveil the chemical and dynamic processes at work in the Jovian atmosphere. The teams will rely on advanced modeling, capable of simulating swirling movements and heat transfers between the different layers. Each parameter will be compared with Juno's readings and the infrared spectra from James Webb. Upcoming scientific publications will detail the mechanisms of haze formation, its evolution, and the relationships between storms, cyclones, and auroras. NASA and its partners hope to extend this collaboration, especially since the James Webb instruments, maintained at very low temperatures to ensure their sensitivity, remain fully operational. Juno, for its part, continues its polar revolutions, studying the gravity, internal structure, and winds of the planet. Future missions to the icy moons will rely on this enriched atmospheric mapping. Thanks to the observations from 2021 and 2022 focused on infrared and extreme phenomena, researchers today have a solid foundation of knowledge to tackle the forthcoming challenges of Jovian exploration. The infrared renaissance driven by the James Webb, reinforced by Juno's measurements, shows how cooperation between different observers transforms our understanding of gas giants. The auroras, fascinating in their luminous variety, become major clues to magnetic activity and internal dynamics. The haze, long perceived as a mere veil, appears as a key factor in atmospheric chemistry. As for storms, they are now observed from the base to the highest altitudes, gradually revealing their mechanisms. In 2023, the news around Jupiter took a new turn. 12 additional satellites were discovered, bringing the total number of known moons to 92. This announcement, relayed by the American media PBS, sets a new record and rekindles interest in this complex celestial population orbiting the most massive planet in the solar system. With a diameter more than 11 times that of Earth, Jupiter possesses a zone of influence capable of attracting objects of all sizes. These discoveries are the fruit of methodical observation campaigns conducted by astronomers who compare images captured over several nights. To better understand this process, it should be recalled that a satellite is a natural body in orbit around a more massive celestial body. Researchers use very sensitive telescopes to spot small luminous points moving around Jupiter. By tracking their movement over several weeks, they can confirm their nature. Some moons, described as irregular, follow highly inclined or retrograde orbits. Others, closer to the planet, are regular and orbit in the same direction as the Jovian rotation. The validation of a discovery requires several observations to rule out any artifact or confusion with an asteroid. The milestone of 92 moons confirms the complexity of the Jovian system. It includes emblematic bodies like Ganymede or Europa, but also a multitude of more modest objects, sometimes measuring only a few kilometers or a few miles. Their study could reveal clues about the history of Jupiter's formation and its surroundings, dating back to the origins of the solar system. Many of these small moons might be remnants of ancient collisions, occurring millions or even billions of years ago. They are of particular interest to scientists because they may preserve traces of the initial conditions of the protoplanetary disk. In this climate of scientific excitement, a major event marked the year 2023, the launch of the space mission called Jupiter Icy Moons Explorer, often abbreviated as JWST, with the acronym in English meaning Jupiter Icy Moons Explorer. Conducted by the European Space Agency, this probe took off on April 14, 2023, embarking on an ambitious adventure. This project, prepared for several years, aims to explore the icy moons like Europa, Ganymede, and Callisto. These bodies of substantial size could harbor liquid water oceans beneath their frozen crusts, potentially favorable for the emergence of microbial life. To provide a more precise idea, the JWST probe is an imposing spacecraft, equipped with sophisticated instruments designed to explore the surface and environment of the icy moons. It carries high-resolution cameras capable of revealing the smallest reliefs, as well as spectrometers that analyze light at different wavelengths to identify the composition of the ices and the possible presence of organic materials. A penetrating radar complements the package, designed to probe the ice in depth. The objective is clear: to determine the thickness of the ice layers and detect possible pockets of liquid water to deepen our understanding of these distant worlds and their potential to harbor life. When talking about these icy bodies, it's important to recall that their surfaces are subjected to extremely low temperatures, reaching several tens of degrees below zero or several tens of degrees Fahrenheit below zero. The surface of Europa, for instance, drops to minus 160 degrees Celsius or minus 256 degrees Fahrenheit. Yet at depth, internal heat might maintain liquid oceans, heated by gravitational interactions with Jupiter and between the moons. These phenomena, called tidal forces, cause deformations in the frozen crust, generating heat. This would explain the presence of salty water beneath Europa's surface, where a mix of water and minerals would remain in a liquid state. On April 14, 2023, the JWST probe lifted off from a launch pad in French Guiana, the European Space Agency's launch site. The timing was chosen to take advantage of the favorable alignment of celestial bodies and the orbital mechanics necessary for reaching Jupiter. After distancing itself from Earth, the rocket embarked on a long journey lasting several years. Gravitational assist maneuvers, which involve using the attraction of Earth or Venus, will increase the probe's speed without adding to its fuel load. This type of interplanetary navigation is essential for optimizing trajectories to the most distant regions of the solar system. The JWST mission has several key scientific objectives. It will first precisely map Ganymede, the largest moon in the solar system, whose diameter exceeds that of Mercury. Analyzing its internal structure could confirm the presence of a core, generating its own magnetic field, and its interaction with Jupiter's magnetosphere. Next, the probe will focus on Europa, considered a promising candidate in the search for traces of microscopic life. The visible cracks on its surface suggest exchanges between the underground ocean and the ice, paving the way for the study of organic compounds via the plumes or surface deposits. Finally, Callisto, although less active, could offer a glimpse into the ancient history of the Jovian system, thanks to the preserved traces in its crust. Even though directed by the European Space Agency, the mission is part of an international dynamic. American, Japanese, and other researchers are participating in the development of instruments, as well as the collection and interpretation of data. This cooperation illustrates the worldwide interest in exploring the Jupiter system. In parallel, NASA continues its own programs in this region, but the launch of JWST in 2023 marks a decisive step for Europe in the realm of distant planetary missions. Upon its departure, the probe also carried communication and power systems capable of withstanding extreme space conditions. As it approaches Jupiter, it will face intense radiation and one of the most powerful magnetic fields known. Engineers have planned specific protections to preserve the electronic components, solar panels, and scientific instruments exposed to the charged particles of the Jovian magnetosphere. This technological challenge is all the more crucial as the mission will span several years, the time needed to fly over the moons and collect a maximum amount of data. The mission's timeline is already partially established. Once the navigation phases are completed, JWST will reach Jupiter's environment in the first half of the next decade. Excitement grows as the arrival approaches, especially since it will coincide with the enthusiasm generated by the discovery of new satellites. Some scientists believe that the current list of 92 moons could grow thanks to advances in telescopes and increasingly precise imaging technologies. Many observatories, on Earth and in space, are now capable of spotting tiny celestial bodies orbiting the giant planet. For the curious, it might seem surprising that so many moons remain to be discovered around such a massive and observed celestial body. Yet, the vastness of space, combined with the small size of these irregular objects, makes them difficult to detect. Some measure only a few kilometers or a few miles and blend into the brightness of Jupiter. Observing them often requires several nights of follow-up, and it is not uncommon for a suspected object to be ultimately disqualified. The confirmation process is long, but each validated discovery is greeted with enthusiasm. reinforcing the public's interest in space exploration. The year 2023 will be marked by a double advancement, the increase in the number of known satellites around Jupiter and the launch of the JWST probe. This coincidence is all the more significant as Jupiter plays an essential role in the dynamics of the solar system. It influences the trajectories of asteroids and comets, protecting Earth indirectly. Studying its environment sheds light on many aspects of planetary formation and possible extraterrestrial habitats. When JWST arrives on site, it will also serve as a relay for potential future missions and transmit unprecedented images of the icy moons. Researchers hope to gather detailed information about the shape of the ice caps, water movements beneath the ice, the structure of Ganymede, or the composition of Callisto. These observations could answer key questions. How does water remain liquid in such a hostile environment? What organic compounds might exist there? Is there a sufficient energy source to sustain a form of life? These are fascinating questions that will fuel scientific news in the years to come. The cooperation between teams and participating agencies is crucial to orchestrate each step. The probe will conduct flybys at specific moments, combining sunlight with observations in different wavelengths. These data will allow the creation of precise geological maps, measure local gravity to detect any anomalies, and verify the presence of oceans beneath the ice. Each pass must be meticulously calculated, as the trajectories are influenced by the gravity of Jupiter and its moons. It will also be necessary to avoid radiation belts that can damage even the most resilient equipment. In the scale of space history, the year 2023 stands as a milestone in our understanding of the Jovian system. The confirmation of 12 new satellites enriches an already impressive inventory, but the arrival of JWST opens a new era. It will allow a better understanding of the internal mechanisms of the moons and their amazing potential. For scientists and the general public alike, this adventure promises unforgettable images and perhaps one day, the discovery of a microscopic form of life in a remote corner of this icy universe. Thus, 2023 becomes the year when Jupiter surpassed the milestone of 92 moons identified, while JWST embarked on an extraordinary mission. For the general public, it's an opportunity to rekindle fascination with this majestic planet, visible to the naked eye, and to become aware of its gravitational influence. No matter the outcome of the research, this exploration already captivates minds. Other enigmas await resolution, bringing with them new insights into our place in the universe. The story is just beginning for JWST and Jupiter. The next chapters will be written in the shadow of the frozen moons, possibly revealing a hidden marine world beneath the ice, where science and dream meet to bring us closer to the mysteries of the cosmos. In this year, 2024, the exploration of the Jovian system continues to captivate scientists and the curious. Carried by a meticulously prepared voyage marked by technical achievements, a dual international effort is unfolding to push the boundaries of our understanding of Jupiter and its moons. The first mission, JWST, is set to execute a crucial maneuver on the 20th of August. The second, led by NASA's Juno probe, plans a fascinating flyby of Io, the most volcanic of the Jovian moons, in December. Let's adopt the perspective of a scientific documentary to delve into the detailed narrative of these major events. To grasp the stakes, we must first understand what a gravity assist flyby is. This technique allows a spacecraft to use the gravity of a celestial body to modify its trajectory without tapping into its fuel reserves. In our case, it's the moon and then Earth. Comparable to a cosmic slingshot, The method involves skimming a massive object to exploit its orbital speed and space-time curves, thus offering an energy boost to the probe's orbit. It is one of the most eloquent examples of human ingenuity applied to the exploration of the outer reaches of our solar system. JWST, developed by the European Space Agency, was launched in April 2023 to study Jupiter's icy moons, Europa, Ganymede, and Callisto. In August, it will benefit from a double gravity assist flyby, combining the Moon and Earth. This astronomically rare configuration, due to its precise alignment, will provide the necessary thrust to reach Jupiter while consuming minimal fuel. The success of this maneuver depends on extreme precision in trajectory calculations. To achieve this, engineers simulate detailed scenarios, integrating the rotation of the Earth, that of the Moon, and the ideal moment for the probe to be exactly where it needs to be at the desired time. The slightest disturbances, such as the gravitational influence of a minor object, must be anticipated and corrected in advance. The narrow passage of JWST near our planet and its natural satellite, scheduled for August 20th, will save the equivalent of about 150 kilograms or 331 LEBs of fuel, thus avoiding a precious propellant burn. This saving will extend the potential duration of the mission, offering more flexibility for orbit adjustments around Jupiter. Once there, JWST will still need to refine its trajectories to study the icy moons in detail. These worlds remain major scientific targets. The space agency aims to verify the presence of internal oceans and explore their potential habitability. Each kilogram or 2 lbs of saved fuel represents a valuable asset in this long journey. The August maneuver thus symbolizes both precision and collective ambition in the service of planetary science. Meanwhile, Juno continues its mission around Jupiter. In orbit since July 2016, after a launch in 2011, this probe, initially planned for a brief mission, has been extended several times due to the excellent health of its instruments and the interest of the discoveries made. It has already offered spectacular images of the planet, brilliant cloud formations, polar cyclones with unprecedented structures, and crucial data on the interior of the gas giant. In December, Juno will perform its 65th close flyby of Io. This satellite, unique in the solar system for its volcanic activity, features a surface dotted with calderas, craters, and lava lakes over 1200 degrees Celsius, or 2,192 degrees Fahrenheit. These incandescent expanses, in perpetual motion, sometimes cover areas as vast as terrestrial metropolises. This extreme volcanism results from tidal forces exerted by Jupiter and nearby moons, causing internal stresses that heat Io's crust. This flyby holds great scientific importance. With its sophisticated instruments, Juno will be able to map the surface in several wavelengths and photograph the lava lakes with great precision. The thermal data will also be essential for analyzing the temperature of these structures and understanding their internal dynamics. The goal is to better understand the geological structure of Io, a world where intense activity could enlighten us about mechanisms common to planets subject to strong gravitational interactions. The upcoming images could reveal previously unknown details: crust deformations around volcanic areas, the renewal rate of lava lakes, or gas plumes rising hundreds of kilometers or miles high. Juno will then have the opportunity to capture these phenomena in visible and infrared light during one of the closest and most ambitious passes of its mission. It is important to remember that these flybys often last only a few moments. It is during these brief windows that the instruments must operate at full capacity, collecting as much information as possible before the probe is carried further by its orbit. This is why each maneuver is meticulously planned well in advance. The slightest error could compromise lighting conditions or the quality of the data collected. The challenge is to graze Io at a sufficient altitude to obtain precise images while protecting the probe from radiation and high relative speed. The data expected in December is also part of a global scientific strategy. Researchers will cross-check Juno's observations with those of other missions, notably JWST, to create a consistent picture of geological activity around Jupiter. Even if JWST is not directly focusing on Io, comparisons between the satellite and the icy moons will help identify factors favoring intense volcanism, or conversely, the formation of a frozen crust. Images and data from Juno will help refine theoretical models of Io's internal structure. Simulations will allow estimates of the heat generated by friction, the depth of magma reservoirs, and the thickness of the crust. The chemical composition must also be analyzed, particularly the high presence of sulfur, responsible for the iconic yellow-orange color of its surface. The lava lakes, in turn, could reveal the presence of basalt or other silicate-rich materials. The spectrometric analysis that will follow will provide an unprecedented glimpse into the mineralogy of this restless celestial body. Beyond scientific objectives, December 2024 promises a spectacular moment for the general public, with the broadcast of images in near real time on the platforms of space agencies. From Earth, even the best telescopes struggle to reveal Io's details. Volcanic activity there is difficult to perceive from a distance, and only a probe placed very close can reveal all its richness. The next flyby of Juno should thus offer a new perspective on the most volcanic moon in our solar system, where lava shapes often surreal landscapes. Space exploration is not only about science, it is also a shared spectacle, an adventure where each image becomes a source of collective wonder. At the same time, the coordination between JWST, Juno, and any other missions that will explore Jupiter in the coming years shows how much space exploration relies on close collaboration. Agencies plan together to exchange data, adjust instruments, and take advantage of orbital alignments. The success of the combined Earth and Moon flyby scheduled for August 2024 will allow JWST to gain speed, while Juno will relentlessly pursue its operations around Jupiter. While JWST accumulates orbital energy, Juno will observe Io with the hope of better understanding the secrets of its molten mantle. These two missions will embody both the diversity of scientific objectives and the complementarity of approaches implemented by different space entities. The achievement of gaining 150 kilograms, or 331 lbs of fuel, thanks to the gravitational maneuver scheduled for August 20, 2024, must be praised. Such a propulsion advantage allows for an extended mission, offering more flexibility for the future. In space, every kilogram of fuel counts, especially hundreds of millions of kilometers or miles from Earth. Ground teams will undoubtedly experience moments of intense tension during this delicate operation, monitoring flight parameters live, controlling the angle of passage closest to Earth and the Moon, adjusting the trajectory in case of deviations. The first signals of success, which will take a few seconds to reach us, will bring immense relief to the control centers. In the following months, attention will turn to Juno. The teams will anxiously await confirmation that the probe followed the ideal trajectory to approach Io very closely. The margins for maneuver are narrow, as Juno is already evolving in a hostile environment, subject to intense radiation and unstable gravity. Each instrument will need to be precisely coordinated for the 65th flyby. Sunlight must be perfect, and cameras aimed at the most active area of Io, where previous flybys have revealed vast lava lakes. Forecasts suggest images of glowing flows, releasing their smoke on the surface, while new magmatic flows will emerge from the depths. If all goes as planned, the scientific findings of December 2024 will be invaluable. Understanding how a small celestial body like Io can sustain such intense volcanism for billions of years opens the door to new theories about the internal energy of planets. This concerns not only Jupiter and its moons, but also potential exoplanetary systems hosting similar satellites. Earth volcanoes and geophysicists will see parallels to explore by comparing Io's mechanisms with those of terrestrial volcanoes like those in Hawaii or Iceland, despite differences in size, composition, and dynamics. It is through this precise choreography, orchestrated in August 2024 for JWST and a few months later for Juno, that the extent of what we can still learn is sketched out. A constantly evolving solar system is revealed, where each mission extends the lifespan of the spacecraft, optimizes every resource, and allows for concrete advancements. Whether it's the composition of lava lakes or a gain in fuel efficiency, these results will lay the groundwork for future explorations. 2024 may only be a step, but it perfectly illustrates the philosophy of space exploration. To move forward cautiously, equipped with the experience gained to get a bit closer to understanding distant worlds. The flame of human curiosity, ignited by Galileo, still burns bright, fueled by each flyby, each observation, each image from the heart of the solar system. From January to the end of May 2025, the Juno probe, in orbit around Jupiter for several years, went through a particularly dense and exciting phase of investigation. The main focus was the 69th close flyby of the Jovian atmosphere, with the aim of capturing precise images and collecting unprecedented data on the planet's deep layers. This mission, conceived and led by NASA, aimed to better understand the evolution of Jupiter's winds and internal structures. For months, engineers and scientists adjusted parameters in preparation for this strategic flyby, likely to shed light on certain still poorly understood climatic phenomena, such as polar cyclones or the Great Red Spot, clearly visible from Earth. Ground teams checked everything to ensure that instruments like the color cameras and magnetic sensors were operational as the crucial date, set for late January, approached. On January 28, 2025, Juno finally made this 69th pass, approaching to only 58,000 kilometers or 36,040 miles from Jupiter's upper clouds. This distance, tiny on the scale of the giant planet, nevertheless allows the different layers of the atmosphere to be seen with striking precision. In the following days, a series of images is transmitted to Earth. Among them are spectacular views of the northern latitudes, where cyclones with vibrant colors form almost geometric patterns. These gas vortices, similar to terrestrial hurricanes but on a gigantic scale, spin around low-pressure centers and create fascinating shapes. The public, captivated, discovers them on scientific outreach platforms and official space exploration sites. It's a major advancement for Juno's instruments, capable of delivering visual data of remarkable quality despite extreme conditions. But the interest does not stop at the surface. Researchers are looking to find out what lies beneath the cloud layer, invisible to the naked eye. During this flyby, Juno's instruments measure the composition of gases, the thermal distribution, and the wind velocity at different depths. The initial results reveal that these winds, already known for their intensity, remain powerful over several hundred kilometers, or 621 miles. The shock comes a few weeks later, with a publication in the journal Nature Astronomy. According to this study, based on Juno's data, so-called cylindrical winds would descend up to 3,000 kilometers, or 1,864 miles beneath the surface. Imagine vast rotating columns of gas, moving as a uniform block, forming giant structures. This phenomenon could explain the colored bands visible on Jupiter and provide clues about the heat generated in the planet's inner layers. These results captivate the scientific community, intrigued by the ability of these winds to persist at such depths. On rocky planets like Earth, the density of matter and the internal structure naturally limit air circulation to the upper layers. With Jupiter, the rules change. Mainly composed of gas, the planet descends into complex transition zones, without offering a solid surface comparable to that of our world. Some researchers suggest that the immense amount of hydrogen and helium would eventually form an extremely dense fluid in depth. The cylindrical winds, organized around the axis of rotation, would then play a role in thermal redistribution and energy balance on a global scale. Nature Astronomy reports that Juno's gravimetric measurements reveal an uneven distribution of mass, reinforcing the idea of a complex internal dynamics. Each flyby brings us a little closer to these deep mechanisms. During this same period, from January to May 2025, another celestial body attracts the attention of the Juno mission, Io, a major moon of Jupiter. Io has long been recognized for its exceptional volcanic activity, its surface constantly being reshaped by powerful eruptions and sulfur plumes. Before modern probes, this effervescence was only partially known, often reconstructed by modeling. The regular flybys of Juno, as well as previous missions such as Galileo or Voyager, have provided a remarkable set of observations on Io. The effects of gravitational interactions between Io, Jupiter, and the other moons are now identified as the primary source of intense internal heating, responsible for this constant volcanic activity. On May 7, 2025, an article published on Forbes' website confirms, thanks to in-depth analyses of Juno's data, that Io remains the most volcanic body in our spatial neighborhood. The new images reveal gigantic lava lakes and volcanoes so active that they temporarily alter the moon's atmosphere. The scale of the phenomenon is such that, over a short period, recent flows entirely cover older zones, radically transforming the landscape. Scientists can now follow the evolution of these eruptions almost in real time by comparing shots captured with each passage of the probe. This constant monitoring has made it possible to identify new volcanoes, as well as cooling and heating cycles, directly influenced by the gravitational forces imposed by Jupiter and neighboring moons like Europa or Ganymede. One of the major revelations from this campaign lies in the diversity of volcanic manifestations on Io's surface. On our planet, volcanoes respond to a relatively standard structure with a magmatic reservoir and an eruptive conduit. On Io, the pressure exerted by orbital tensions is such that eruption points can move, fragment, or merge over time. The sulfur plumes reach several hundred kilometers or miles in height and leave deposits in bright hues, between bright yellow and deep red, evoking unreal decors. The temperatures detected by infrared far exceed those observed on Earth, although mitigated by the extreme conditions of space. It is the interaction between internal frictions, orbital forces, and gravitational tides that compose this unique geological landscape. The confirmation of Io's intense volcanism, relayed by Forbes, arouses interest from both specialists and the general public. The images captured by Juno of unprecedented precision reveal sinuous flows, visible faults, and craters likely to be filled or disappear within a few weeks. Seismologists are considering the consequences that these internal movements could have on the moon's stability. Some propose models showing the formation and disappearance of volcanic reliefs on the scale of thermal cycles. These discoveries, supported by Juno's data, lay the groundwork for future missions specifically centered on Io, with the aim of better understanding the internal processes behind this enormous energy. Although Juno was designed to explore Jupiter, its four main moons have remained at the heart of the scientific project. Each flyby has been an opportunity to enrich knowledge about these satellites. Due to its activity, Io fuels many hypotheses about the thermal behavior of celestial bodies. Some even extrapolate these observations to refine our understanding of exoplanets composed of volatile elements. During each passage, Juno captures data on the composition of Io's atmosphere and the effects of its volcanism on the local magnetic field. The coincidence between the 69th flyby, the publications in Nature Astronomy, and Forbes' statement constitutes a striking snapshot of the richness of this research on the Jovian system. Technically, coordinating a close flyby of Jupiter with data collection on Io requires extreme precision. Engineers must contend with the spacecraft's rotation speed, the intensity of the magnetosphere's radiation, and its orientation relative to the Sun to ensure energy supply. Each passage brings its share of information while exposing Juno to extreme conditions where charged particles can interfere with the instruments. Despite these constraints, the period from January to May 2025 promises to be one of the most fruitful. Researchers praise the quality of the images and the diversity of the measurements, covering both Jupiter and its moons. The winds in the upper atmosphere and the intensity of Io's volcanism dominate scientific and media discussions. In spring, as the northern hemisphere of Earth emerges from winter, Juno has already transmitted an impressive amount of data. The Control Center is planning the next research campaigns, one of which will likely focus on cylindrical winds. The aim is to determine whether they sink beyond the 3,000 kilometers, or 1,864 miles measured, or if they split into distinct layers. Numerical models based on fluid dynamics principles adapted to the gigantic pressures of Jupiter attempt to simulate these circulations. Unlike Earth, where the crust limits internal exchanges, Jupiter allows for a fluid movement of material under pressure, creating immense spirals visible on its surface by colored bands speeding at several hundred meters or yards per second. Observations from the 69th flyby give unprecedented weight to these theories. Meanwhile, the spotlight on Io's volcanism, abundantly relayed in May, contributes to raising public awareness of the Juno mission. Discoveries about the planet and its moon paint a striking picture in which internal heat and gravitational forces orchestrate an unexpected cosmic ballet. Io, unstable and dynamic, even injects matter into the Jovian environment. Its eruptions propel chemical particles that, on escaping, manage to join certain layers of Jupiter's magnetosphere. Ongoing studies explore the effects of these contributions on overall magnetic dynamics. The Forbes article highlights how our solar system still holds many mysteries. Io, in particular, plays the role of a natural laboratory, openly exposing phenomena invisible elsewhere. From January to May 2025, the Juno mission thus marks a decisive milestone. Between the stunning images delivered on January 28th, the analyses published on Jupiter's deep winds, and the official recognition of Io's extreme volcanism, the period marks a triple advancement. Educationally, these results help spark interest in major themes. On one hand, the atmospheric dynamics of a gas giant, and on the other, the rapid geological evolution of a moon heated white-hot. For many researchers, these months show that the exploration of Jupiter and its moons is far from complete. Many questions remain, whether regarding the planet's internal structure, the operation of Io's volcanoes, or the formation of deep winds. The coming years, fueled by new flybys and other missions, will undoubtedly provide answers. At the end of these months of intense activity, scientists have gained a clearer view of the phenomena at work beneath Jupiter's clouds and on the surface of Io. The Jovian system appears as an ever-moving ensemble, channeling considerable energy into every corner. The cylindrical winds, akin to vast swirling columns, reveal an integrated mechanics where planetary rotation, gravity, and chemistry intertwine. Io, for her part, maintains her status as the champion of volcanism, relentlessly altering her landscape and exposing new magma at a dizzying pace. This striking contrast between Jupiter's dynamics and Io's upheavals gives the Jovian system an almost theatrical character, a planet with swirling guts, a moon in continuous change. Thus, the interval from January to May 2025 underscores the importance of the Juno mission in understanding Jupiter and its entire environment. Publications in reference journals and their echo in the media reflect a convergence of efforts to broaden our view of the mechanisms at work in other stellar systems. October 14, 2024, will mark a decisive date for space exploration. On that day, the Europa Clipper probe, developed by NASA, is set to launch towards the moon, Europa, orbiting Jupiter. This mission aims to uncover one of the greatest mysteries of the solar system, the possible existence of a liquid ocean beneath Europa's icy crust. Before reaching the gas giant, Europa Clipper will undertake a key step, a flyby of Mars, scheduled for March 1, 2025. This maneuver, called gravitational assist, will allow the probe to accelerate thanks to the attraction of the red planet while reducing its fuel consumption and the duration of the journey. To better understand, one can imagine the spacecraft sliding along the curvature of space-time around Mars, like a slide, taking advantage of the gravitational energy captured during the flyby. Once this step is completed, the probe will continue its journey toward Jupiter. Its arrival is expected in April 2030, after a nearly 6-year journey. Upon its insertion into Jovian orbit, Europa Clipper will undertake a series of 49 close flybys of Europa. During each pass, it will approach within a few hundred kilometers or a few hundred miles of the icy surface. Thanks to advanced instrumentation, including a radar capable of probing the ice and very precise cameras, the mission will analyze the internal structure of the moon, evaluate the salinity of the supposed ocean, and measure the thickness of the crust. Scientists estimate that exchanges between the underground water and the seabed minerals could create an environment conducive to the emergence of chemical reactions essential for life. Ground teams will monitor potential signs of fissures or geysers that might indicate water rising to the surface. This ambitious project relies on numerous technical innovations. The probe's power supply, ensured by solar panels, has been designed to function despite the low luminosity present in Jupiter's vicinity. Large antennas will transmit a massive volume of data to Earth. An ultra-precise navigation system will guide the flybys, avoiding any danger to the onboard instruments. In anticipation of the intense radiation in the Jovian environment, the electronics have been specially shielded. At the end of its flybys, Europa Clipper is expected to deliver the most detailed study ever conducted of this icy moon. shedding new light on one of the great scientific questions of our time. Can we imagine conditions favorable to life on a world so far from the Sun? Starting in 2026, a fascinating sequence will open around Jupiter's icy moons. While Europa Clipper intensifies its exploration, the JWST probe, acronym for Jupiter Icy Moons Explorer, developed by the European Space Agency, will also reach the Jovian system. This dual rendezvous will give rise to an unprecedented scientific synergy. JWST's observations, centered on Ganymede and Callisto, will enrich those of Europa Clipper. Together, the two missions will produce a geological mapping of remarkable precision, reaching sometimes 50 meters or 164 feet per pixel. A major progress compared to the images previously sent by Voyager or Galileo. These maps will help identify fractures, ridges, icy plains, and potential deposits from eruptions, whether volcanic or cryovolcanic. Interest in these icy moons extends beyond just American and European agencies. China is currently developing Tianwen-4, a project aimed at exploring the Jovian system, although its details remain to be clarified. Building on the success of its previous lunar and Martian missions, China is gradually asserting its presence in the distant exploration of the solar system. Its objective, to complement the investigations carried out by other space powers, offering a new perspective on Jupiter and its satellites. Meanwhile, NASA is studying a project called Io Volcano Observer, targeting Io, the closest moon to Jupiter among the 4 satellites discovered by Galileo. Io is the most volcanically active body in the solar system, with frequent and spectacular eruptions. Close observation of this activity would provide a better understanding of the moon's internal dynamics, as well as allow comparisons with other volcanic worlds, whether within our solar system or beyond. Studying Io would also offer valuable clues about how the combined gravitational forces of Jupiter and its neighbors maintain a constant internal heat, transforming Io into a true geological cauldron. Between 2026 and 2035, a decade rich in discoveries is expected around Jupiter. The JWST and Europa Clipper missions will conduct an unprecedented joint exploration, allowing cross-comparisons between the magnetic fields, atmospheres, surface compositions, and internal structures of the moons Ganymede, Callisto, and Europa. Researchers will then be able to determine whether these bodies have shared similar histories or followed different paths. For the first time, we will have access to detailed data on the workings of the deep layers of these frozen worlds, on the potential presence of internal oceans, and on their interactions with Jupiter's dynamic environment, characterized by an intense flow of charged particles. When we cross the horizon of 2035, the exploration of Jupiter and its entourage of satellites will reach a decisive turning point. The data collected by Europa Clipper, JWST, and possible international missions will have transformed our understanding of these distant worlds. They will also pave the way for studying other gas giants beyond our solar system. Today, thanks to the transit method and radial velocity measurement, astronomers have revealed the existence of planets nicknamed hot Jupiters, massive exoplanets similar to Jupiter, but orbiting so close to their star that their temperatures reach several hundred degrees Celsius, hundreds of degrees Fahrenheit. Analyzing our own Jupiter allows us to approach these extreme environments. By comparing their formation, internal structure, and atmospheric dynamics to those of a more temperate giant, we refine our planetary science models. Conversely, some cold giants are located far from their star, like the famous 51 Pegasi b, called Bellerophon, at the time of its discovery. With technological advances in telescopes and observation instruments, researchers hope to better characterize these distant worlds, even detecting the components of their atmosphere and signs of internal or magnetic activity. As knowledge progresses, Jupiter also establishes itself in the collective imagination. It occupies a central place in many works. British composer Gustav Holst dedicated an entire passage to it in his orchestral suite entitled The Planets. In this piece, Jupiter embodies joy, abundance, and cosmic majesty. This vision is directly inspired by Roman mythology, where Jupiter reigns over the sky and the deities. In cinema, the giant planet is also fascinating. It appears in 2001, A Space Odyssey, the cult film by Stanley Kubrick, which already raised many questions about the mysteries of the Jovian system. More recently, the series The Expanse envisioned a future where Jupiter, its moons, and its resources become power issues on a solar system scale. This fiction, grounded in realism, depicts how humanity might one day establish outposts around the gas giant. These representations illustrate the allure that Jupiter holds over our imagination. Its vastness and the enigma of its moons, some active, others potentially habitable, continually fuel hypotheses and stories. For those who are just discovering planetary diversity, confronting the richness of the Jovian system can spark genuine curiosity. The idea of ocean worlds, such as Europa or Ganymede, raises fundamental questions. They touch on biology as much as cosmic chemistry, because the possibility that life could emerge elsewhere pushes science to reinvent itself and extend its boundaries. Looking further ahead, a global cooperation could arise to pierce the icy crust of Europa or Ganymede with automated systems capable of exploring deep waters in search of microscopic organisms. Similarly, Io's volcanoes could be subject to close-up observations, perhaps even from a dedicated orbiter that would follow live the sulfur eruptions and silica-rich plumes. Some missions might choose to establish a long-term presence around Jupiter, like the Cassini probe around Saturn, staying attuned to the slow and unexpected developments of this complex system. Regarding exoplanets, the next generation of observatories, whether infrared or even more sophisticated, will aim to identify elements such as water vapor, methane, ammonia, or carbon dioxide. These substances, well known in Jupiter's atmosphere, will serve as benchmarks for the study of distant worlds. In this respect, Jupiter will remain our point of reference. It remains the best-studied gas giant with its titanic storms, its powerful magnetic field, the complexity of its atmospheric flows, and the influence of its many satellites. Understanding how this planet withstands the colossal forces that drive it enlightens us about the potential stability of similarly sized exoplanets. Finally, it is possible that the exploration of Jupiter, combined with advances in propulsion technologies, will make this planet a strategic step for future interplanetary missions. Already today, its immense gravity is considered as a relay to reach more distant destinations. Perhaps one day we will see probes or even crews make a stop in its vicinity before continuing towards Saturn, Uranus, or Neptune. Thus, beyond 2035, projecting even further, it appears that Jupiter and its moons will continue to fuel our research and our quest for discovery. Imagining a future where we pierce the ice to reach unexplored oceans testifies to the power of our creativity. The coming revelations will redefine our place in the universe and enrich the dialogue between science, art, and imagination. As our understanding of the Jovian system progresses, its influence will grow, inspiring dreamers of tomorrow to look up to the sky and ask, what lies beneath this frozen surface? And if, somewhere, a form of life awaited discovery. It is this prospect that continues to fuel collective enthusiasm as the countdown is underway for Europa Clipper, JWST, and all the missions set to cross the frontiers of the unknown.